Cambridge, late 1967. A 24-year-old graduate student, Jocelyn Bell, is combing through miles of chart paper by hand when she notices a faint smudge that keeps returning to the same patch of sky, ticking once every second and a third. Bell had helped build the telescope with Anthony Hewish, a sprawling field of antennas designed to study quasars by watching how their radio signals flickered. Nothing in the radio sky was supposed to pulse this fast, this precisely. Every day, the instrument spat out roughly 100 feet of chart recording, and Bell read all of it herself. Among the expected flicker of distant galaxies, one signal refused to behave. She called it simply Scruff. The Scruff kept a stubborn schedule. It appeared 4 minutes earlier each night, meaning it tracked the stars, not the sun or any earthly transmitter. Whatever this was, it lived far beyond Earth. When Bell and Hewish looked closer, the pulses were metronomic, one every 1.337 seconds, steady enough to rival a clock. No known natural object pulsed that quickly and that regularly. They ruled out radar, television, satellites, faulty wiring. The signal came from a fixed point among the constellations and swept past on schedule, night after night, immune to every earthly explanation they threw at it. For a few uneasy weeks, they entertained the obvious wild idea, an alien beacon. Only half joking, they labeled the source LGM-1, Little Green Men 1. A regular pulse from deep space demanded a serious answer. They seriously discussed how you'd announce contact with an alien civilization to the world. The answer had been sitting in the literature since 1934. Astronomers Walter Baade and Fritz Zwicky had proposed that a dying star could collapse into a city-sized ball of neutrons. For 3 decades, almost no one took it seriously. Then Bell found a second pulsing source, and a third, and a fourth, in completely different parts of the sky. 4 separate alien civilizations broadcasting on the same frequency made no sense. This was Nature. In February 1968, the team published in Nature. The press needed a word for these pulsing radio stars, and one stuck: Pulsars. A new kind of object had entered the catalogue. Within months, Thomas Gold and Franco Pacini nailed the mechanism. A pulsar was a neutron-star, the collapsed core of a dead star, spinning at blistering speed and firing beams of radio waves from its magnetic poles. The spin comes from simple physics. When a massive star's core collapses, it shrinks from something the size of the sun to a sphere barely 20 kilometers wide, and like a skater pulling in her arms, it spins up violently. That 20-kilometer sphere can rotate several times a second. Its magnetic field, trillions of times stronger than Earth's, channels radiation into 2 tight beams streaming out from the magnetic poles. The magnetic poles rarely line up with the spin axis, so the beams swing around like a lighthouse. Each time a beam sweeps across Earth, we catch a pulse. Miss the beam, and the pulsar is invisible to us. That lighthouse picture explains the timing perfectly. What it doesn't fully explain, even now, is how the beams are generated in the first place. The exact physics of a pulsar's radio emission remains unsolved after more than 50 years. Pulsars don't only shine in radio. NASA's Fermi Gamma Ray Space Telescope has found scores that pulse in gamma rays, including Geminga, a nearby pulsar that is nearly silent in radio, but blazes at the highest energies. The most famous sits inside the Crab Nebula, the wreckage of a supernova Chinese astronomers, recorded in 1054. The Crab pulsar spins about 30 times every second, and its beam flickers from radio all the way to gamma rays. Astronomers have now catalogued more than 3,000 pulsars, listed in databases like the ATNF Pulsar Catalog. The Vela pulsar, another supernova remnant, spins about 11 times a second and is among the brightest gamma-ray sources in the sky. A young pulsar bleeds energy as it spins and slowly winds down. The crab is slowing by a tiny fraction each day, and that lost rotational energy is exactly what lights the surrounding nebula. Measure the slowdown, and you can estimate the pulsar's age. But the slowdown isn't perfectly smooth. Every so often, a pulsar suddenly speeds up in a glitch, evidence that beneath its solid crust lies a superfluid interior, a frictionless ocean of neutrons that occasionally dumps its spin into the crust. In 1992, Alexander Wolszczan and Dale Frail found something around pulsar B11257+12 that shouldn't have survived: planets. At least 2 rocky worlds orbiting a stellar corpse. These were the first confirmed planets ever discovered beyond our solar system, circling not a sun, but a pulsar. The first planets ever found beyond our solar system didn't circle a star. They circled a corpse. Old pulsars should fade. As they spin down over millions of years, their beams weaken until they slip into a graveyard and go dark. Yet astronomers kept finding ancient pulsars, spinning faster than any young one. In 1982, Don Backer and colleagues found PSR B1937+21 rotating 642 times per second, a millisecond pulsar, its surface moving at a sizable fraction of the speed of light. An old dead star had somehow been wound back up. The culprit is a companion. If a burnt-out pulsar has a nearby star, it can siphon gas off it, and that in falling matter spins the neutron-star back up to hundreds of rotations per second. Astronomers call these recycled pulsars. Some recycled pulsars then destroy the very star that revived them. Black Widow and redback pulsars blast their companions with radiation, slowly evaporating them. The fastest known pulsar, PSR J17482446AD, spins 716 times a second. A single millisecond pulsar is one of the steadiest clocks in the universe, some rivaling atomic clocks over years. That precision turned pulsars from curiosities into instruments, tools for testing the deepest laws of physics. In 1974, Russell Hulse and Joseph Taylor discovered 2 neutron stars orbiting each other, one a pulsar. The system PSR B19132216. Its ticking let them track the orbit with extraordinary accuracy. The 2 stars were spiraling inward, losing energy at exactly the rate Einstein's general relativity predicted if they were radiating gravitational waves. It was the first proof gravitational waves existed, and it won the 1993 Nobel Prize in Physics. An even better laboratory came in 2003, PSR JA7373039, the double pulsar, where both neutron stars beam toward Earth. It remains one of the most stringent tests of general relativity ever built by nature. If one pulsar makes a good clock, dozens make a detector. Since the 2000s, collaborations like NANOGrav have monitored an array of millisecond pulsars across the sky, timing their pulses to within billionths of a second for years on end. In June 2023, NANOGrav announced the payoff. Across 15 years of data, the pulses were all shifting together in a faint, correlated pattern. The fingerprint of gravitational waves stretching and squeezing the space between us and every pulsar at once. These aren't sharp bursts. They're a low, continuous hum in space-time itself, thought to come from pairs of supermassive black holes circling in distant galaxies. To detect it, astronomers turned the entire Milky Way into a single instrument light years across. Every pulsar in the sky right now is being stretched by gravitational waves too faint to otherwise detect. The same precision has a down-to-earth use. In 2018, NASA's Sextant experiment aboard the NICA telescope used pulsar pulses like a cosmic GPS, letting a spacecraft in orbit determine its own position. using only the ticking of dead stars. Jocelyn Bell was left off the 1974 Nobel Prize that honored Hewish for the discovery she made. Decades later, she won a $3 million breakthrough prize and gave every penny of it away to fund students from underrepresented backgrounds. More than half a century on, we still can't fully explain how a pulsar's beam is generated. The emission physics that started this whole story is still unsolved, and the faint nanohertz hum now surfacing in the timing arrays hasn't been traced to a source. Merging supermassive black holes are the leading suspect, but nothing yet rules out something stranger, and only the next decade of timing data will settle which it is.